All right, I think we can get started. So welcome back, everybody, to another webinar. Today we have an interesting topic that I don't think we've even mentioned before. I don't think it's even appeared on our Slack. So it's an interesting branch of interpretability work called computational mechanics. And so it's my pleasure to introduce to you today's speaker, Mateusz Piotrowski. Mateusz works on interpretability of LLMs, primarily on attribution methods. And he also co-created the open source circuit tracer library by Anthropic. He has also worked on computational mechanics and applying them to transformers, showing that attention implements constrained Bayesian belief updating. Quite hard to understand this phrase when you say it out loud, but this is precisely what we are here to understand today. So without further ado, Mateusz, the mic is yours. Thanks.
Thank you. Okay. Yeah. So hi everybody. So the title of my talk is called Predicting the Predictor, in which hopefully I will manage to explain to you what the hell the comp mech really is. So yeah, like the basic idea is, like Kuba mentioned, it's like you could call it a branch of interpretability, but that might offend some people. I guess what we understand as interpretability mainly is this thing when we take like a trained model, like a true language model, and we try to like look inside into the computation, and maybe we need to like simplify the computation, decompose it in some way into like some parts that we can actually understand. So we can do some probing, we can look at the SAEs, and then we try to like look at the interactions between those representations, maybe by doing things like attribution or like circuit tracing. And then we like look in the model, like on some task, on some behavior, try to like really narrow down from like the sea of possible things that the model can be doing, just like really zoom out on this one thing and try to understand it and explain it. And usually we're like successful to like varying degree, right? We get like a lot of answers that like seems pretty satisfying, but like very rarely they're like exhaustive. So the idea of doing the computational mechanics, which really happened before even we started training the large language models, it was really a science of like, what does it even mean to do a prediction and what does it mean to do it optimally? So instead of like trying to attack, this very large and complicated thing at once, we start from something much smaller, from a small process that we can understand. We use that process to generate the data, and we train our model, trying to predict that data, trying to like replicate what the model is doing, basically trying to like parrot the process. But at the same time, we can like figure out what does it mean. How would I, like knowing how the data was produced, how would I try to predict that optimally? What would be my best guess? And that can like answer us to some like intermediate question. Like, okay, I try to like know what the next token is, like what do I need to remember? What do I need to like have in my memory? We can also know things like, okay, is this model that we train actually doing as best as it can, or like can you actually do better? So yeah, I mean, in the sense, it's just like the idea of studying, like, given a process, what would the parrot look like? But like when we try to do it for the language model, our parrot, it's like, it turns out it's pretty weird. And you can really try to like have this reductive statement of like, it's just trying to repeat the data. But it turns out to like actually repeat the data well, you need to do something really complicated, and in many cases the thing that you need to do is more complicated than the process itself. So I think trying to like come up with description on what does it mean to like predict language optimally, it's really, really difficult, and we won't be trying to do that. More so if you like think about a language as a process, which we won't get into like in this talk, it turns out it has like a lot of very weird properties that we don't quite know how to think about at once. But you can also think about like the predicting language as an ensemble of like many smaller tasks that maybe we can like understand in isolation. So yeah, I mean, instead of trying to like attack everything at once, maybe we can start with something that's less weird than that and do something that's like much less intimidating. So just to give everybody an intro, and do not expect that's going to be like useful for understanding the language for you, but just to like give the intuition of like how does the work look like when you're trying to do CompMech. I would like to introduce you to like very simple process called random XOR. And the idea for this process is very simple. You can write out HMM for this model that could generate the data. You can write a program to generate the data. It's going to be very short, because the idea is basically you sample two random numbers, you flip a coin twice. That's your two symbols that you emit, and the third symbol that you're going to emit going to be an XOR of those two symbols that you just emitted. So for like the HMM that we're looking at, it's if we start in like any of the random states, so like let's say we start in like S0, we flip a coin, we got a 1. We start in the middle. We flip a coin and we get out to one of those states. We flip a coin again and we get to the next state. So like depending on the path that we took, so here we took like 1 and 0. Okay, an extra of them it's 1. We back in the like initial state and we start over. And this process is very simple, but already you can like notice a couple interesting properties, about it. So when you try to predict that process, it's like, let's say you come back home and there's random XOR generating symbols, and you start looking at those symbols. How do you predict what the next symbol is going to be? I already told you a story, about like how to do it, but like you cannot just say, oh, it's going to be 50-50, because you don't know at which point you started observing the process. So the first symbol that you're seeing might be an XOR of the two previous symbols, or it might be a random symbol. You don't really know. So what needs to happen for you? You need to see enough symbols of this process such that you can disambiguate in which step of the process you are. And to do that, you basically try to start with your initial guess of like which state you are. And this is what you have on the left side here. On the bottom, we have like the legend that describes all of the states. And like initially we think we're like in the mix of all of the possible states. Your guess, like for the initial states, is basically based on the steady state of an HMM. So like, where would we be on average if we like simulate this process like for infinite time? And then you see the first symbol and you see 0. So right, that already, if we go back to the HMM, that already like reduces the number of states you could have been in, because you weren't like in the ST, right? So that will go to 0, like because this state cannot emit 0 at all. So you could have been like in any one of the other states. Most likely, because you saw a 0, you were like in this state, like this state's probably gonna increase the most, because this one can only do zeros, or the other way. I'm like actually now confused where the probabilities are.
Can I have an objection to, because if the bits are chosen at random, then you can always guess optimally by always outputting the XOR of the previous 2 bits. You cannot do better than chance of predicting the inputs, and if the inputs are random, then any prediction will take half of them good, right?
Okay. Yeah. So maybe I wasn't like clear enough. Because like actually, so initially, yes, you are right. Your first prediction, like as you go in and you just think what the next symbol gonna be. Your actual prediction it's random, yes. It's like you don't know what's gonna be. Like it's 50-50 between like 0 and 1. But after you saw 0, then you can say like, okay, I saw a 0. So like there's 2 chances of what could have happened. I might have gone from like one of the random states to the other states, but that doesn't help you. So like you are in like SF or like ST, you don't know in which you are. So your guess is still like random for those 2. Or you like exited the like initial state, the middle state, in which cases also your guess is random. So for the first for the first number, like yes, it's still random. But like as you keep observing the symbols, right? Like you see another 0, and then you see 1, and there's only one chance that like this was actually like now you know that your next symbol now you know that your next symbol needs to be 1. So this is the probability of the next symbol, right? So after you observe this sequence of like 0, 0, 1, 0, you know that your next symbol have to be 1. And we call this that like you are synchronized to the state. Because from now on, you actually predict optimally because you know at which position do you have you had your like you have your XOR.
I'm just saying that unless you use like Breyer scoring to penalize overconfident predictions, then you don't need to be synchronized.
Yes, I'm not sure I understand why you wouldn't want to be synchronized, because like in every case, it is beneficial for you to be certain, and there are prefixes which are gonna disambiguate at which position the XOR of the 2 previous bit happens. And the XOR is the only deterministic part of this model. So like once you know when the deterministic thing happened, you can just say for certain what the next symbol gonna be. Otherwise, you need to guess. So like, you know, it's gonna be
yes.
like.
So how do you penalize overconfident guesses?
I'm sorry, you don't need to, I don't understand why you do want to penalize something here.
I'm just saying that if you don't penalize overconfident guesses, then my guesser that always outputs the XOR of the previous 2 tokens is going to perform optimally.
That is not true.
Why?
Just because. So let's see, where in the sequence we could like, where's the XOR of them?
If it's
So
not
I'm
true,
sure that
then
in the top example, actually, in the top example, it's actually, let's see. So here, 0, 0. An XOR of that is 0, right? So like you could predict here with like probability of 1, I'm sure that like the next one gonna be 0, but this is not true. The next one gonna be 1, and this is valid for this process because you don't know at which point you started observing this process. So in this case, it's not optimally to output an XOR. And the other thing is like maybe we're confused. We are predicting, which is like we are not inputting the symbol.
Then the starting position is, if the starting position is chosen adversarially instead of randomly, then maybe it's true, but
no, the position is started randomly. Like the process has been going for some time. You just come in and start observing it at random point in time. It could be any position, but you don't know if you're on the XOR. And like by observing the sequence, you can understand when the XOR is gonna happen.
How can you guess a random bit better than 1/2?
Because you know at some point it won't be random. Because you know that like, oh, like you could try for this sequence to shift where you think the XOR is, right? So like you can do your guesses. So like you could say that this position was an XOR of the 2 previous ones. This is not true. This is contradiction because like, oh, you say like, I think this is going to be XOR, so you predict it's going to be 0 with probability of 1. No, the symbol is actually 1. So I know I wasn't in the state that's actually, I wasn't in one.
Yes, but this is giving me an adversarial sequence and not choosing the.
No, it's just like you can. There's no adversarial sequence. There's only like sequences.
It is adversarial because you just chose one adversarially.
No, I'm just describing a sequence that could be sampled from the model. So this sequence is possible to be produced by the model.
Yes,
but there are also sequences that are impossible to produce by this model. So there's like, yes, thank you. Yeah, let's leave it till the end.
So you are not trying to predict a sequence. You are trying to get a model that produces all sequences.
Yes, the random model that we have can produce all of the possible sequences. We know that we're observing one of the possible sequences, and then we're trying to guess what is like the optimal distribution over all the next symbols. And sometimes we know that like, okay, the next symbol needs to be 1 and it cannot be 0. But cool. Yeah, sorry about that. Let's move on. Just like as a counterexample, the thing that I wanted to say is like in the example above, we can, based on the prefixes, disambiguate when the XOR is going to happen. But like we can see just zeros forever. And this is also like something that could be produced by this model. And it is possible that we're going to see zeros for a long time. And then like we don't get any information that would allow us to basically do that prediction that is like deterministic. So we still need to like keep guessing where we are. And eventually we just like hopefully going to start seeing ones. And we need to see ones that like, if we just see a single one, we still not, then we can like have two guesses. Sorry, we can have one guess when the XOR could be. But yeah, it's a simple process, but it has like this very interesting property of synchronization. And like, if you actually just remember, you know, when you synchronize you can like, from that point on, you can like predict with optimal probabilities until the end. Cool. Now let's move on to a different process that we actually did work on, which is different from random XOR in the sense that for random XOR, you have a limited number of the belief states, which means like I didn't introduce you to the concept of belief state, but basically the belief state is an idea of like, what is my belief distribution over like all of the possible states of that HMM? And in the case of random XOR, the number of configuration is limited, it's finite. But you can also have processes in which like the number of possible sequences is infinite. So here we have this like process called MES3. The idea here is also very simple. We start in one of the random states, and we start, and at every time step, we can transition to any other state with some probability. We parameterize this process by X and alpha. And basically, X tells us what is the probability that we're going to change the states. And if we don't change the state, we just stay. And in every state, we emit a symbol. And the symbol is like a noisy clue about where we're at. Because the every state is going to emit its own symbol with probability alpha. And it can emit equally likely the symbols from the two other states. So like, it's not like you're seeing a symbol, you don't know where it came from. It's a hint. At every time, it's a hint where you were. And then you can like guess, oh, so like if I were there, this is like where I probably would go. And you just keep playing that game, trying to guess. And the thing that you can do here, it's like, you start the process. If you try to compute it, your like steady state for this process is like, you could be equally likely in every state. So your belief distribution over like which state you are in is this dot in the middle. This is your belief state. Now, what can happen is like, let's say you're observing A and you say, aha, it's A. And let's say the alpha here is 85. So you say, I think I was in the state A, so, and then like you can transition, but let's just simplify this a little bit. I was in the state A, so I take a step here. I was probably in A. Then you see symbol B, but then you think like, I was in A, so it's now this combination. Like, was it because I saw a noisy symbol from A, or did I transition to B and I saw a symbol from B? And that's going to move you to a different point. Now, depending on the parameterization of this process, all of those dots, all of those steps that you can take, gonna move. And here I have like all of the possible places you can get to by playing that game in 10 steps. If I reduce alpha, I'm gonna be less confident about which state that came in from, because the observation is gonna be more noisy, which means like actually my step's gonna be less confident. I can get to something like 0.3, which means, like I'm seeing symbols, but they're like equally likely to come from like any state. The other thing you can do is like, we can set X to 0.3, which is gonna have the same issue of like, yeah, I saw some symbol, but like I could have gone anywhere. It doesn't like really tell me anything, which is this like the two not interesting cases. But other than that, you have a really rich family of geometries that you can see from this model as you just try to map all of the possible belief states that you can have from over this model. Not everything is possible. It's only a subset. But the cool thing about this process is like this, the way you move around this is like self-similar. So it produces like very beautiful fractals, which is one reason why this process is cool to work with. But also the geometry here is non-trivial. Cool. So the thing you can do is to take this process, and we just like write a short Python program to work like what I just described. And we generate some sequences from that. We can generate like, we can just keep sampling the batches of data from that. And the sequence is gonna just like, look like the sequences of like 3 symbols. And we do the normal like language model training procedure. We know that the process that we created, we know like what kind of geometry we would expect in that model. And it turns out that like, yes, actually, if you just take the activations of this model, activation at like every step of the model, like the activation of the residual stream after seeing like 2 tokens, gonna correspond to to some belief state, right? And it turns out we can train a linear map that's just gonna map from like all of those residual vectors at like different prefixes to different like coordinates in the simplex. It's even better than that, because it turns out you can just take the activations of the model, stack them, run a PCA of them, and it turns out they like live in 3 or like 2 dimensions. And you can just plot them, and you literally get the same thing that we just saw. You literally get this belief state. There's other cool thing that you can do, because like we can look after the MLP. This is a single layer transformer. We can look after the MLP, but we can also look just after the attention. And we have just a single attention head. It turns out if you do the PCA of the activations at this point in the model, you get a Sierpinski triangle, which is also very cool. And okay, those things are pretty, but the question is like, what the hell is going on? And why those shapes are so regular? And like, why does, the representation in the model reduce to that? And it turns out that like, yeah, it does happen, and it keeps happening, for like different configuration of the model. We can configure our process in many ways, generate the data, and then we can look like, what kind of representations we're gonna get. So here we always have the intermediate, which is sampling after the attention for different configurations, and here we have like sampling after the MLP, and the same on the bottom. One thing that I wanted to show you, I think really cool thing about this process is like what you can do is you can make the alpha be the opposite. So like as I'm like emitting a symbol, it's not telling me which state I am in, it's telling me which state I'm not in, because like we can set the alpha to 0, but you have a lot of intermediate, like very cool states that you can see in this model. And then you can see that like, oh, I'm seeing a symbol, but I'm not taking a step to A. I'm taking a step, to a combination of like, I saw a C, so I'm taking a step somewhere between those two guys. And there's an interesting thing like that you need to change in the model to be able to represent that. Cool. So just to recap, what we're looking at here is on the activation side, it's just the PCA of the model activations, like just plotted. That's literally all it is. And on the left, it's like what we would predict. What's the shape we would predict they would have to take. And now we can ask, how does it happen in transformers? And like one maybe not immediately obvious thing, it's like, it is actually confusing how the models do that, because the idea that I described before of how this works is like we have our belief states. We saw some symbols and we have our guess of like which of the generating states we are in. And the way it normally works is like you see a next symbol and you update your previous guess. So like the way it works is, we started in the middle, we're like super uncertain, but like we saw a symbol, so we took a step here. And then we saw another symbol, so we take a step from here to the next step. But that requires you to have a memory, which RNNs will have, but Transformer won't. Transformer only have the KV cache, and KV cache allows you to have like only look limited number of steps back before like making the prediction. So yeah, like Transformer, like let's say we have 2 layers, then like okay, the first token position computed this representation, but to look back at it, you need 2 layers. So like the other layer can like access the thing that was there after the NLP, because otherwise it can only access the tokens. And this is what I looked into, like what is going in here. And it turns out there's like this very interesting algorithm implemented by the transformer, which I will try to explain, but it will require some interpretability knowledge that I don't know if folks are here familiar with. So I will try to simplify this. But the idea is like we have the attention model, which does a linear projection of the token, which gets us this thing called OV vector. And this is the thing that we will try to use to build up our representation from. So our 3 tokens, they get like each one gets like an arrow in a way. And the way how we're gonna do this, we're gonna try to reconstruct the triangle by at every token from scratch, trying to like add them up in such a way that we land on the point where we need to land. So in the token, like in the first, we just see single token. Okay, we just take a single step here. But then after we saw 2 tokens, what we do going from backwards, we have an attention pattern that's gonna promote always the most recent token. This one gonna get the most attention. So we're gonna take a step here, and then we're gonna take a step in the other direction. This is like how I added them up. You can like add them the other direction also to see the same thing. But basically every time you use your OV vector to from scratch take like a combination of those vectors with the attention pattern that's always gonna be like the same, and you can compute exactly what is the attention pattern that you're gonna expect. And it's always just like taking a weighted sum of those vectors gonna like land you on the triangle where you need to be. And then like the next step is actually we haven't mapped it as exactly, but this is just like when you look at the representation in the space is you actually the only thing you need to do to go from the Sierpinski triangle to the thing that we actually need is to twist it. Like imagine you just like grabbing here by the corners and just like stretch it. And this is what MLP gonna do. MLP just gonna learn that like space transformation for you to get there. And it turns out it's everything you need to like represent everything from the top row. And I can like add more layers to the transformer. It's always gonna do the thing in the first layer. It's always gonna have this same attention if you like train your model successfully. The next layer is just gonna like do maybe small changes to the geometry, but like they won't matter because you already get like very good prediction at layer 1. But there's a thing about like, I just said it has a single attention head, which gives you this thing that like, cool, I have this pattern is always positive. So I have only 3 vectors, and that gets you like the figures from the top row. It turns out if you have this thing when like, oh, the symbol that you're emitting telling you where you are not, you need by construction 2 attention heads, and otherwise you are not able to represent that. And the reason for that is like when you do the math, it turns out that the attention that you need is like oscillatory. So we need both the positive and the negative component of that. And what happens is like when you have 2 heads, it's basically one of them going to be performed as the positive part and the other one's going to perform as the negative part. And you also get the extra vectors to basically construct your intermediate representation, which in this case is like this really nice like snowflakey structure instead of Sierpinski triangle. Cool. And I think the nice thing about this is like, we can actually say that, yeah, we do understand what happened in this simple case as a satisfying story. It doesn't tell us a lot about language yet, but, you know, hopefully like understanding that is like, we can actually internalize what does it mean for transformer not to be able to do recurrence, but still do pretty good, because there exist different methods of representation that are available to transformer, and you know which of them are available really depends on like what kind of architecture do you have. But we know that the thing that we like, if you have a lot of attention head and you have some LMOPs, we don't like, this is pretty damn expressive, and we can like keep asking the question, why is it? Fun fact, like when you try to do random XOR, it's actually different, because the LSTM gonna work perfectly, gonna learn all of the synchronization and so on. But the transformer won't ever like get to the perfect thing, because if you start like, if you synchronize the transformer and like start feeding it zeros, transformer will always forget which was like the XOR position if you just try to train it naively. So there's more to find there. But so far, and like, I would like you to present the other work that that was also done in CompMag, but I think it's a little bit more complicated. So I will just show you like a little simplification of like what I'm gonna be talking about. Before we like were talking about these processes that had like a finite number of states. So if you have finite number of states, you have finite number of corners in your simplex. So we can like think about it this way. But it's very important to internalize. This is not the only way to think about it. So what I have here for you is like a process that has infinite number of states. We have an arm of a clock that we can move around. And moving that arm will always give us a different probabilities of like where we're at. So like saying that we have an arm over here means that we're gonna sample, you know, one of this like NESW symbols. And then let's say we have some rule that like after sampling a symbol, the arrow is gonna move somewhere else. And we generate data this way. And we can also like teach a transformer to predict those sequences and see how well it's gonna get. But the problem with that is like, you cannot represent this as HMM, because this thing has infinite number of states. You can just like slice it very finely and just get more accurate and more accurate representation. But like, you need to keep growing your representations to an infinite size to get like more accurate. And this is just example of a process that is not represented by classical theory. And there's another work which goes, it's also a mouthful. It goes something like transformers leverage nominally quantum and post-quantum representation, which sounds very fancy. But the idea is you have different processes which have very different representation than the simplex. And using our knowledge from like quantum physics, we actually like those were like initially like discovered for quantum physics. But we can also just, it's once you sample from those processes, it's also just, you know, a sequence of symbols that you feed to the transformer, the same way like feed, you know, tokens from the language. And then you look like which kind of representation do you find in the model? And turns out you can actually find the representations that we use in like quantum physics, you know, or like in some cases also like post-quantum. And I would say like this work is pretty dense, but I think it's like pretty interesting. We know some of the representations of the data that are pretty useful, but we probably should expect that like there might be representation of the data that we don't even yet understand. Though I don't know how it's likely. Maybe it's like a combination of things that we already figured out. We just need to understand that. The other really cool work that was also done recently is, I like this a lot. It's imagine the thing that I described to you before, but now let's just try to combine a couple processes. So again, we have our like programs that like generate, you know, the sequence of symbols for every one process, but like what we're trying to train our transformer on is not those like individual processes. We just take a product of them. So the model still just sees a sequence of symbols. We know that we created the sequence as a product of the other ones, but what's going to happen is like after you train that process and you look inside the model activations, you find that the model is actually representing each of those factors separately. And you can actually find orthogonal subspaces in the like activation space that like each one gonna have, you know, the process that it came with. And like here it's like the combination of the processes that we looked at, but also like the other processes that require the different kind of representation. Yeah, you can actually find that like, so here's like how they looked in the theory. Here's like exactly the kind of figures that you get if you just recover them from activations. The thing is like it will still get the factors even if you just try harder to like make it not be exactly coming from those processes. So like even if you add some noise to the data and you try to like, okay, now you actually need to learn the combined thing to learn, you know, to learn everything pretty well. The model like won't care. It will like still, if it's like, if the noise is like small enough, even if the model has the capacity to represent the full thing, it will still try to like learn the factors, which I think is pretty cool. And like maybe gives us a hint of like, oh, maybe we can like, maybe this is how we should think about what the model is trying to learn when representing language. Cool. And yeah, I think this was the last thing I wanted to show from the results. That should just be really honest. And I think some people have been thinking that in the back of their head. Yes, this is very toy models. This is simple examples. We don't think it's going to give an answer to what the models are doing. And this work is complementary to the actual interpretability. We assume here that like we predict optimally. We are not predicting the language optimally. Like the models are very capable, but not that capable. Myself, I also like started working on interpretability, but the good old-fashioned one. But the hope here is like by doing this kind of work and having like this really fundamental understanding, we can like build up vocabulary of like what should we look for in the transformers. Because the thing that we're working on right now is literally just like this one paper on superposition that we had back in the day. But we're seeing this cool thing in transformers. Like we can see that days of the week seems to be arranged in a circle. We see that when we try to do the line breaking task in the language model, for some reason it's being arranged on a spiral. And this is kind of question that I think could be answered with CopMech. Like, why does it happen so, and does it has to be this way? And like maybe when does it stop being true? And yeah, that was all from me. Yeah, thank you so much. And I think we are ready for questions now.
Yeah, thanks very much, Mateusz. Please join me, everybody, in clapping for Mateusz virtually. Yeah, questions from the audience.
So how do you match the predicted distribution versus ground truth besides looking at pictures?
Oh, so for the processes that I showed, the optimal prediction, you can actually just compute it with like pretty simple math, especially like I'm familiar with the HMM case, in which you have the like optimal update to your beliefs after seeing each symbol, right? So like, given that I believe, I'm equally likely to be in each state, I see a symbol, so I know I'm like a little bit more likely in A. And then the only thing I need to do is like, okay, I know what is the like output distribution in every state, so I just like take a weighted sum of that. So like I weight the emission distribution of every state by like my belief that I'm in each of those states, and this is like the optimal way to predict. I don't know if that makes sense. Even like in the simplest case, like let's say that the A state always emits A and B and C, like they all just have a single symbol. And then like the optimal prediction is literally just my belief over state. If I think I'm like 50% chance of being in A and 50% being in B, then my optimal prediction is like 50% for those two symbols.
I think Marcel had a question in the chat, but I can't see it anymore. Maybe he deleted it.
Oh, there's just like question about the presentation. This is literally just Claude Code and HTML. I think it's time for us to move past PowerPoint, and I don't see a reason to do LaTeX anymore, but maybe I'm wrong.
Okay, yeah, it's interesting.
Is there a paper we can read?
Yes, which I think I can just send the list to Kuba. I think the good place to start with a lot of interesting papers, and there's two categories of paper you can read. The recent papers, which are on, let me
Something went wrong and you got muted.
I'm back. Sorry about that. Yes, two kinds of paper. The recent one, which concerns transformer, I just recommend everybody to check out Simplex. And if everybody wants to get involved, it's also good to reach out to those guys. Let me know if you like introduction. But there's also more fundamental papers from again, Compaq is older than transformers. And there's a lot of interesting stuff from Crutchfield about the epsilon machine, the different kind of processes, the different kind of things you can measure about the process, and so on.
So let me ask the obvious and slightly provocative question. What is the usefulness of this for AI safety? What is the theory of change?
Yeah, I guess it's like basically the same as interpretability. I think the worry is, okay, we have this, our best guess is not good enough, and there is much better guess of what we should be looking for to understand what the model is thinking about available, and we should just try to figure out what it is. I think there's a fair criticism of that, which is, yeah, we're trying to think about the optimal prediction a lot. Are you sure you're more likely to contribute to safety than capabilities? Maybe you just figure out there's this one thing in transformer, it's super annoying, and the model just tries to work around us those way, but we could just switch that thing and it's gonna be fine. And that turns out just makes the model much more powerful very quickly. But my answer to that is just I don't know, we just pretty successful by increasing the capabilities right now.
I didn't even mean the dual use thing. My question was more like, we started doing Mac interpret, say 3 or 4 years ago, and there was this big pivot from Neonanda's team to pragmatic interpretability, right? So instead of trying to reverse engineer the full neural network, they're now basically saying, okay, here's a linear probe, and we can use this linear probe in production for Gemini 3 or whatever, right? I don't really see the immediate equivalent of something like a linear probe that comes out of this, but maybe the right way to think about it is how you said that, like, interpretability is going off of this paper about superposition, right? And don't really know what questions to ask. So maybe the theory of change for this research agenda would be like trying to figure out what the hell are good questions to be asking.
I think the other thing maybe worth pointing out, I think they're like pretty decent at like mind reading of the model. I don't think like I think SAEs being unsupervised are like still pretty good. I think logic lens are pretty good way to like looking at like what the model is thinking about. There are many ways in which you can like try to answer that question. I think what we're like doing worse job at is like even the thing that Circus are trying to solve, which is like how does the model do the computation? And I think if we had like better understanding of like what are the kind of things that the model's actually trying to do, or how does the representation work beyond just like, oh, this linear direction, they like interact, maybe we can just develop much better methods. And that would like allow us make statements more of like less of the form like model is thinking about this. It's like more like, oh, in those circumstances, model will think about this and then do that. Yeah, but I think nobody really is like looking for like full reverse engineering. We just think like, okay, that understanding really will allow us to take a bigger chunk out of the problem.
Yeah. Any other questions? Okay, I wanted to also ask about like language prediction, right? Because you've shown us hidden Markov models, and that's all fine. It's like basically what I'm trying to understand is how things like temperature come into play here, if at all. So if I the underlying generating process of language is very different to a hidden Markov model that can be encompassed with like 2 lines of mathematics. And so, like, if I was to try to do this sort of stuff on LLMs and actual natural language, I might be saying something stupid, but would I have to perform all the experiments with like temperature equal to exactly 0, or does temperature, is it even relevant for these experiments?
I think so. Yeah. So like a temperature equals 1. You basically use the optimal probabilities to like sample your next token from. Like for a lot of the processes that I showed, it's like literally you can like if you set temperature to 0, like you collapse really quickly. You get like a sequence that's like really not probable from the model because like the A is the most likely, and like if you just say I'm just gonna always pick the most likely token, you're just gonna like go further and further and like believing like, oh, I'm always in A. So the way to think about the temperature is like, if like if we're using temperature 1, we're using our best guess of what the actual language process is. It's like what does like our parrot learn to do. If you use temperature 0, I think this is something about language. You just get like the part of that process. You can like imagine a process that's like a mix of stochastics and like deterministic part. If you say temperature to 0, you basically get only like the deterministic part of the process, which again, like for our language model, is not truly the deterministic part of the language because we didn't actually learn the language.
I see. Okay, last chance to ask questions. Okay, well, if there are no further questions, then let's thank Mateusz once again for his very interesting and nicely prepared HTML presentation. Was it HTML?
Yeah, it was HTML.
Yeah, it was HTML. Okay, yeah, cool. Thanks again, Mateusz. This was very interesting. Before you all go, I will drop the link to the next webinar, as always, in the comments. It's going to be May 14th by Julia Bazińska. So Julia works at this company called Lakera. They have this thing called I think Gandalf, which is like an arena where you can try to jailbreak a model, do a prompt injection or something, and they collect real life examples of attacks. I think they collected 200,000 instances of people trying to jailbreak the model, and they're doing analysis of what those interactions look like, what are the common jailbreaking methods and the sort of stuff. So we're gonna switch from CompMech to, I guess, adversarial ML and safeguards. Thanks everybody for coming today. Thanks Mateusz once again, and we'll see you in 2 weeks.
Thanks.
Thanks.